Today we are seeing how just updating a subset of the model weights can improve performance compared to the Karpathy GPT. I'm actually going to compare this. This is compared to what I made a byte pair encoding Karpathy, which I still need to make a video on how I made that. It's just taking the original GPT Karpathy video and applying knowledge from his tokenizer video to set this up. But we'll start out with the results, and then I'll go into how it was made. Okay, so here we'll start with the results of the BPE Karpathy. So here at step 5000, got a training loss of 1.71 and a validation loss of 1.88 roughly. Okay, so it's 7.1 and 8.8 at 5000. And then I did a few different things. It's only in certain spots that we'll do this. Okay, so it was 7.1, which compares to 1.67. So 1.67, the subset of weights beats it. 1.82 also beats on the validation loss. And all right, now let's get into it. First off, I applied it only to, okay, so we got a update ratio of 0.6. So the subset of weights, 60% of the weights, roughly, are how many we updated. Not on all different parts, though. If we go into it here, it'll be in this one. Not this one. No, yeah, this one. Okay, so we only did it in the heads. In the linear linear layers of the heads. So that would be the, okay, so we're in the head, the key, query, and value. So only updating 60% of these guys. I've played with a couple things. I still need to play with more. I tried, where is it at? I keep losing it here. Initialize. Okay, so we just did heads. I also tried heads and the feed forward. That reduced performance, but if you just do feed forward, just do heads, I think just do feed forward, which was this one, 1.78, 1.91. How does that compare? So 1.78, there's 1.78 at 4000 compared to up here, 1.79 at 4000, roughly equivalent. So this was the BPE Karpathy, had the 1.79, and that is roughly equivalent to the 1.78. So you can reduce in the feed forward, which is not as many weights that you're reducing. But if you use the heads, which is the keys, the queries, the values, it reduces a lot more, as well as reduces your loss. If I did both heads and feed forward, you get 5000, 1.76, which is actually less than 1.71. And now there are other ones to play with. There is we'll get into how this is coded up here in a second. But there is, okay, so there's the head stuff. We already did that. There's this projection layer in multi-head attention. You can try with that as well. We did the feed forwards, the ones in the feed forward. And then there is another one at the end of the transformer that gets applied at the very end of each block. No, not each block. Sorry, at just the very end. Which that could be a huge. If we did this, that could be a huge savings in terms of parameters. Like I said in a previous video, updating this, if we're using PyTorch, you're actually not saving any parameters. You would have to create a custom way of doing this in order to actually save on parameters in time. Or it's not parameters, but be able to speed up the algorithm. I'm going to go ahead and try it with LM head as well. Let's see here, so, and I'll just do that in the background as I go through this. Let that go in the background. Okay, so two things we need. Basically two functions we need. This initialize sparse masks and apply stored masks. So this will happen before you start the training. It's after you set up the model and before you start training iterations. You need the model, you need the update ratio. This for name and module in the model named modules. Basically, we're going to take each module has a name, like the LM head or heads. Let's see if I can find heads. Self.heads equals the module list of the heads. So each one of these self.heads, self.proj, they're all names within the model. And they store those names. So right here we're just going through all the names of the model, which would be like I'll print it out here later after this training run. But it's like it's kind of a recursive naming thing. So you got like transformer or no. So you'd have I don't remember exactly how it is, but if you start with transformer has token embedding, and then once you get to blocks, there's blocks, and then blocks 0 would have a blocks 0.sa, blocks 0.ffwd, and then within that you would have another one named blocks.ffwd.net. So it goes into each one and finds all the layers. So going back to, we're looping through all these names of all of the modules, and we're looking for each module that is a linear layer. And then also, so you pretty much always want those two parts. And then right here is where you can explore which one you want to get to. So looking for in that big old string of a name is heads in it or is lm head in it to find the exact one you're looking for. And then with that, you want the number of weights, number to update, which will be your number of weights times your update ratio. So 60% of the number of weights. It will create a mask of zeros with the number of weights, because you're gonna have zeros for everything you don't want to update, zeros on the gradients for everything you don't want to update, and then we'll apply 1 times it for each one of the ones that you do want to update. Indices are going to be, we're going to permute the, we'll use these indices. It will equal a permutation of the different number of weights. Let's see. Okay, yeah, it does. Okay. From 0 to how many we want, we'll select those to get this indices. And then use those random indices. We'll find the random pieces in mask 1D to set to 1. So mask 1D is going to be zeros mostly, with some random spots in there that will be 1. And that'll be kept throughout the training cycle. And then mask 1D, we'll change it, view as module.weight, which I don't totally know what that means actually. Once again, I did use Gemini to help me out with this. So I honestly don't understand every piece of the code. Let's see, but I assume this just reshapes it or reviews it into the module that you started with. And then I learned what this register buffer is basically going to throw it onto all those name modules and keep it there as a side piece to it, that you can apply, so that it doesn't have to keep constantly recreating this. Okay, so this gets applied. Let's show you where this gets applied. Okay, right here. So right after you make the model, you'll initialize the sparse mass, which is that function that we just had. Need the model, which is the transformer model, and the update ratio, which I have set at 60%. Transformer model is the main one, which I think in Carpathy I have a different name for it. I don't remember. No, okay, cool. So yeah, that's right here. Training iteration starts down here, so it's right after you make the model. And then the next piece, the next function, happens all the way down here. You apply the stored masks on the model, which means, okay, so you go through here and you get the data. You apply the model with the forward to get the logits and the loss. You set the gradient to 0. You do a loss dot backwards, which is going to create the gradients, and then you zero out the unwanted gradients. So this is the inefficient way of doing it, because you create the gradients then zero out the ones you don't want. Whereas if you want to do it efficiently, you would just only create the gradients that you want, rather than zeroing out the ones that you don't want. But this is PyTorch, and as far as I know, you can't do that. But yeah, we'll go to apply stored masks, that function, which is where you apply it, obviously. For module in model.modules, we'll see if it's a linear and has an attribute of the weight mask, which is what we threw in this register buffer up here in the initialize sparse masks function. So does it have this attribute, which is that that register buffer called weight mask? If it does, then if the gradients are not none, module weight gradient data mol. What is that dot mol? I assume it's just a tensor. Module dot weight mask. So we will multiply. Sorry, data dot multiply, which I assume is an element multiplication rather than a matrix multiplication. Yeah, I would assume so. That way that everything that's 0 will multiply with the gradient to get 0, and all the ones will keep as is. Yeah, so that's that. And then I kind of already showed you, but I'll go back through it. All you do is initialize the sparse masks, the first function, right here under the model. And then down here in the training loop, right before you do optimizer.step, you apply the stored masks to the model. That's how you make it. Alright, so let's see how that last one did. So we did both the heads, which is the key, query, and value weights, networks weights, as well as the LM head, I believe. Where is that thing at? Yeah, as well as the LM head, which is the very final layer, which is a big layer. After 5,000 steps, you get 1.766. Not as good as just doing the heads. But how does it compare to the regular Karpathy? 1.766. I guess we could 1.91. We'll look at both. Go up here to this one. Not as good. Definitely not as good. 1.766 versus 1.71. Not as good there. 1.88 versus 1.91. Not as good there. So LM head maybe really needs the full diversity of weights to be updated, whereas it seems like heads itself does not. But yeah, till next time.